Education is the most powerful weapon which you can use to change the world. Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions, providing work and promoted it in 2005. Meet the man, Sri Murray Lakshman Reddy, who ushered in the Silent Mission, a mission to provide technological advancement from time to time, with the aim of imparting education with global standards to enrich values with knowledge in students. Succeeding the paths of Sri Murray Lakshman Reddy, making education a positive experience. Sri Murray Rajashekhara Reddy, Founder Secretary, nurtured MLR Group of Institutions to win the pride of being recognized as one among top engineering colleges in Telangana for the past various industries. Spacious and comfortable classrooms, corridors, advanced laboratories with equipped ultra-modern audio-visual technology auditorium accommodating 1000 plus audience, separate hostels for boys and girls. Each student is specially taken care for the provision of health facilities and hygienic food in spacious and eco-friendly canteen, etc. are salient features of MLR Group of Institutions. AICTE recognized
Good morning, Professor.
Good morning.
Good morning. Good morning. Welcome to International Conference on Advanced Materials for Innovation and Sustainability.
Thank you very much. Thank you for
Thank
the
you, sir.
kind invitation, Arun.
Thank you, sir. Thank you. Thank you. It's my pleasure. Uh, we will wait another couple of minutes to join the participants.
Sure.
So in the morning we had a inaugural session. That will be night for you.
Exactly. I just arrived to office just a couple of minutes ago.
Okay.
We have a little bit of storm here in the Netherlands, so the traffic is busier than usual. And then I was a bit later in the office than usual, so I couldn't follow the earlier sessions today.
Okay, it's okay, sir. No problem.
Powerful weapon which you can use to change the world. Believing in this principle, welcome to Murray Lakshman Reddy Group of Institutions. Providing world-class education and research facilities to help transform people's lives for the better. It is the brainchild of a visionary who conceived and promoted it in 2005. Meet the man, Shri Murray Lakshman Reddy, who ushered in the silent mission. A mission to provide technological advancement from time to time, with the aim of imparting education with global standards to enrich values with knowledge in students. Succeeding the paths of Shri Murray Lakshman Reddy, making education a positive experience. Shri Murray Rajashekhara Reddy, Founder Secretary, nurtured MLR Group of Institutions to win the pride of being recognized as one among top engineering colleges in Telangana for the past consecutive academic years. Situated in vast and peaceful area of 35 acres, students here tend to learn experimenting their life projects through centers of excellence, which is tied up with various industries. Spacious and comfortable classrooms, corridors, advanced laboratories with equipped ultra-modern audio-visual technology auditorium accommodating 1000 plus audience, separate hostels for boys and girls. Each student is specially taken care for the provision of health facilities and hygienic food in spacious and eco-friendly canteen, etc. are salient features of MLR group of institutions. AICTE recognized MLR group of institutions accredited by NAC with A grade and has NBA accreditation for all programs. MLR Sports Complex and inaugurated by MLR group of institutions with most advanced multi-sports facilities like cricket stadium, badminton court, table tennis, billiards and basketball, etc. MLR Sports Complex organizes many national and international university-level sports fests by grooming every aspirant in competing national and international sports forums. Successfully achieved 50 gold medals, 13 silver medals and 16 bronze medals at various national and international sports events. MLR Group providing free admissions every year by supporting aspirant under sports quota with scholarships for the meritorious sportspersons to pursue their career in sports and opportunities in government sectors. To sharpen and extricate students' creativity and entrepreneurial skills, MLR Group has established Center for Innovation and Entrepreneurship with facilities like Social Square, Innovation Hub and Makerspace. The Makerspace is a technical prototyping platform for students' innovation and invention, which is loaded with ultra-modern equipments such as multimedia workstations, 3D printers, CNC machines, laser cutters, and thus provides stimulus for student entrepreneurs. The center has collaboration with various government and non-government ministries for raising seed fund to incubate student projects and startups. This center has developed 8+ market-ready products and supported 11+ student startups. MLR Group has set up livelihood business incubation in association with Ministry of Micro, Small and Medium Enterprise (MSME) to promote new technology or livelihood-based enterprises. Research and Development Cell has 12 centers of excellence in association with various industries and supports faculty and student research. It also has a track record of 25+ funded projects, 700+ SCI or Scopus Journal articles and 35+ intellectual property rights, and the progress continues. In preparing the aspirants to the real-world competitiveness, MLR Group of Institutions has introduced
Scroll down. Will it come full screen? Okay. Down. Okay. Little bit down. Down, down, down. Yeah, that's enough. Okay. Allow only limited people above 50. Good morning, Professor Suleiman. Welcome to International Conference on Innovation and Sustainability. I also welcome all the participants to attend the keynote speech given by the Suleiman. He is a currently is working as a head of the Autonomous Energy Materials Discovery. He is currently working as a head of the Autonomous Energy Materials Discovery and the Dutch Institute for Fundamental Energy Research, Netherlands. So before joining to the DIFFER, he studied before joining DIFFER, Dr. Suleiman studied chemistry at Belkent University in Turkey and obtained his PhD in physics from University of Twente in the Netherlands. Subsequently, he worked as a young energy scientist fellow, first at Harvard University in the USA and then at Leiden University in the Netherlands. During his previous studies, he has been involved with various small and large scale computational research projects on energy materials design. His his group mainly involved in developing the uses of automated virtual materials discovery frameworks powered by the high throughput physics based classical and quantum calculations, artificial intelligence methods, and advanced data infrastructures to accelerate the discovery of molecules and materials for energy applications. His group also involved highly integrated research lines that individually focusing on computation on new battery and catalyst materials design and data-driven method development to accelerate the search for good molecules and materials. So this is all about his short biography of Professor Suleiman. Sir, thank you, sir, for joining us. Now you can take over this session.
Right. Thank you very much for this kind introduction, Arun. And on behalf of you, I would like to thank the entire organizing committee of the conference and giving me this opportunity to present our latest work. I will start sharing my presentation meantime. And I hope you can see it.
Yes, sir, it's visible.
And so this slide needs no introduction. That was a perfect introduction by Arun. So I am Suleiman. I'm a research group leader at the Dutch Institute for Fundamental Energy Research. That is our institute based in Eindhoven in the Netherlands. And I'm the group leader of Autonomous Energy Material Discovery. In the meantime, I am also a Machine Innovation Champion of the Netherlands. Machine Innovation is a large organization who's working on increasing the public funding on energy and sustainability related issues and bringing funding to human friendly projects and research friendly projects. So I also I'm honored to be a Mission Innovation Champion from the Netherlands in the last year. Today I will talk about automating the virtual exploration of electroactive compounds for an efficient energy storage. But before I dive into this topic of energy storage of electroactive compounds, why we need a virtual exploration, let me explain you what we do in our group usually, and how is our approach and what is our research lines. And my group is entirely computational, as you might guess from the name. And by computation, we work on lots of high throughput calculations of quantum chemical calculations, mostly based on DFT, but other semi-empirical methods, as well as classical methods. And that means that we work on different molecules and materials in a high throughput fashion. And we can then generate lots of data that goes into the databases. And when you have lots of data that goes beyond human intervention, then we also make use of the recent popular methods of artificial intelligence applied to chemistry and materials chemistry. From the knowledge that we generate from our AI methods, we guide our computing, and then we try to work on molecules and materials that looks more interesting for a particular application. And our ultimate aim in here is, of course, to develop and automating discovery principle, but in the meantime, work together with experimental labs, so to see whether our predictions are really can be verified in real labs. And this has one advantage, of course, we find new molecules and materials for energy applications. That is fantastic. The second advantage is that by learning from experiments, we can improve our approach to the chemical space, to our approach to computing and our methodology. So we have a way to advance it by comparing the data that comes from experiments. And regarding the research lines, we work on essentially 3 different but highly integrated research lines in my group. These are on battery material discovery, which I'll talk entirely today. And we also work on electrocatalytic material discovery and, as I said, like data science for energy material discovery, which is the integration of AI for the modeling part of the molecules. So in real, it looks like something like this. We work on very different materials, but our approach is very similar. So when we think of materials of 3 dimensions, you can think of like oxides, metal oxides, materials with 2 dimensions. These are like graphene and the other 2D materials, and 0-dimensional materials. Basically, I call these molecules. Which, as you can see, we start with a computational funnel that usually contains lots of candidates, compounds, and then we try to find in the end of this computational funnel the best compounds that can be tested in the lab. But essentially, we try to also formulate a database that comes from these calculations or machine learning predicted materials properties, so that these databases can be useful for further research. And I will talk mostly about the molecules in this talk and the remaining of the presentation. And these materials are all energy-related materials, of course. Why energy can be explained in here. This plot is taken from International Energy Agency, and you can see that the clean energy technologies are taking over the natural gas and coal and hydropower, which are more conventional energy technologies around the world. So we expect that there will be more wind and PV electricity in the future, also in the near future. But we also know that wind and solar power is also intermittent. So in this paper by Aziz and co-workers, they show nicely that when you have a wind supply, you can produce electricity, which is fantastic. When the sun is shining, you can produce electricity when it's fantastic. But the grid, that the usage of electricity by us, by our industry, by our homes, is more or less constant. There is a shift between day and night, of course, but it's more or less constant. So we need electricity almost constantly. So that comes to problem of storing this clean energy in a usable medium, so that we can make more benefit of the wind and solar energy technologies. And that's exactly the topic of today, actually. So today I'm going to talk about 2 different material spaces, and approach is similar. And in the first, I'm going to talk about redox flow batteries. So finding good molecules that we can store electricity in organic and water-based redox flow batteries. In the second and the last part of the talk, I'm going to talk about, again, finding good molecules for sodium-ion batteries. And these are more cathode materials for solid-state batteries. Let's move on to the topic 1. So redox flow batteries. In this animation, you can see that redox flow battery, the liquid is just pumped through a pump from a reservoir to the reaction chamber. And in this reaction chamber, you can then generate electricity by reacting the molecule and depending on its chemical reaction, this redox reaction of oxidation or reduction. And then you can generate electricity, or you can just have electricity used on the molecule in combination with some kind of chemicals. In this case, we are interested in water, so it's proton-coupled electron transfer, actually. The advantage of flow batteries is that they can be made of cheaper materials when compared to more conventional lithium-ion batteries, and they also offer a long cycle life. Redox flow batteries are by no means new. If you think of the technology, it dates back to zinc bromine redox flow battery. that has been invented in the late 18th century, 19th century. And if you look at how this has been progressing, that you will see that so many different chemistries of different batteries, and some of them are aqueous, so that means water-based. Some of them are hybrid systems of aqueous and non-aqueous, and some of them are really non-aqueous systems, so that means that the solvent is organic-based solvent instead of water. In the last years, we are moving on both finding good molecules for aqueous systems, but also non-aqueous systems. And today I'm going to talk about the molecular engineering, because we are interested in small compounds that can store electricity, how we can put electricity on these compounds in an aqueous redox flow battery setup. Why molecular engineering? Because you can think of different molecules that can store electricity, that can be involved in a redox reaction. Then the chemistry is so vast. So there is basically no limit in your imagination of how you can design molecules that can be involved in a chemical reaction that can be taught as an electrical storage material. I am getting some background noise. Is it okay if we can mute the microphone? Thank you very much. So in terms of molecules, when we talk about different properties, redox potential is important, like how this reaction is happening at what potential. The molecule size is important because we want high charge per given size of a molecule. So usually smaller molecules are then better with more reactive sites. Solubility is important because high solubility means that you can put more molecules per given liter of water. That means you have more energy density in your battery. So you don't need to have large tanks, but much smaller tanks can be sufficient for the same amount of energy storage if you can increase the solubility of your molecules. Stability is, I think it's a general issue, not necessarily for redox flow batteries, but for any kind of energy-related application, but also non-energy-related application. So stability of the material that is actively participating in a chemical reaction is extremely important. So we want these molecules to be reversible, so that means that you can put electrons and protons on the molecule and take it back multiple times and thousands of times, so that these molecules should not deform in the water by changing the pH, maybe by changing the heat, with the light, or through time with the presence of maybe other chemicals in the water to increase the electrical conductivity, etc. So stability is a very broad term. Regarding the molecules, we look at two different classes of molecules. The first one is called quinones. The second one is called azoaromatics. These molecules are very similar to each other, although they are different classes. The reaction is also proton-coupled electron transfer, as shown in this diagram. So basically, in the first reaction in the quinones, you can put hydrogen on top of the red colored oxygen atom, and then you can make it a hydroxyl unit on the molecule. And in the azoaromatics, you can put on hydrogen on the nitrogen atom that is embedded in the ring structure of the molecule. And then you can produce an NH group. And both of these reactions are reversible. So that means you can take this proton back. And that means you can, together with the proton, you can take the electron back from the molecule. So then they, in principle, in theory, they provide a means of storing electricity nicely if everything works as shown in this diagram. But the life is not easy, so we have to find always better molecules, better compounds, better materials for energy applications. And how are we going to do that? So the reason that we go on a competition is because in the competition, we can learn, by using quantum chemical methods, we can learn the properties of the material by performing calculations on this material, because we know that the fundamental interactions in molecules and materials are governed by their electronic and atomic structures. So by performing simulations, we know what kind of properties that are relevant to batteries that can be generated, and we also know which materials can be suggested from simulations. And the nice thing about these simulations is that they are usually easy to reproduce in comparison to experiments. So another lab in another piece of the world that can also repeat the same simulations on the computer, on the same compounds, and they can reproduce the results. So that is extremely valuable. If you think of this, this is not always the case for experiments, because there are so many changing factors in the background and experiments. Why do we do high throughput virtual screening? Because we want to study many more molecules and materials as quickly as possible. So that means we have the same calculation methodology on molecules in a large number of molecules in a given time. So high throughput screening is massively parallel. It means that it gives you speed, it gives you scale, the chemical space that you can explore in a given time, but it's also low cost. So if you think of the capital and operational investment in competition is much less than any kind of experiments. So if we can speed up the material discovery process, at least virtually on the computer, then we will speed up the entire chain of material design, which takes usually decades, from the idea to a realization to a commercial product, and realization of as an application in our daily lives. It takes usually decades of research, testing, validation, and then making a product, and then producing it large amounts, and then making it a good price, and then it reaches the customer. So if we speed up the first part where the competition is involved, then we hope to benefit the whole chain of material design by using high throughput virtual screening. And I was telling, because of high throughput virtual screening, we have lots of data. And because of the lots of data, why not use artificial intelligence to produce more meaningful sense of this data? And then use this design and this cycle of a computing database and AI for the study of compounds, for the discovery of compounds for redox flow batteries. So if I revisit the funnel approach that for the redox flow battery compound discovery, we start from top left. In a computer screen, we design a virtual library. That's what we call, so we design molecules. Basically, we draw the molecules in 2 dimensions. And then these molecules, each of them are represented in the funnel as different colored balls. They are different color because each molecule is different. And then we are trying to find which of these molecules can be experimentally tested and validated, that is shown at the bottom left. So how do you design this funnel? How do you start? If you have in the computer so many molecules, where do we start? So we have to look at the properties that are most relevant to the application. In this case, the redox flow battery. So redox potential is extremely important. First and foremost, the compound that you choose has to be an active compound for a battery. Otherwise, it doesn't make sense to be involved in a battery. The second, the solubility that I was trying to explain. If you have higher solubility, that you have more molecules per given liter of water, that means that you have higher energy density. And stability, that we want to address by doing some calculations that can relate it to stability. And in that, we try to find the best candidates. And as you can see, for calculation of redox potential, solubility and stability, there can be different methods that can be integrated in the funnel. For instance, for the redox potential calculation, we use different chemical descriptors, and we perform multi-scale calculations that involves classical, like force field calculations for optimization of the structures in 3 dimensions. And we also involve more electronic structure calculations to get the properties of these compounds that are relevant to the redox potential. And for solubility, there can again be different approaches. You can calculate solvent free energy, for instance, using the calculation principles of quantum chemistry, but also we can use a more data-driven method, like we do in my group, to quickly predict the solubility of molecules, at least to give a trend how a new molecule can be compared to a known molecule in terms of its solubility. Is it more soluble than this one? Yes or no? No, then maybe we should not proceed with this. Yes, then it worth studying it further. And for stability, we look at basically the availability of these compounds on the shelf. So can we directly purchase these compounds? That means that they are made and there is some kind of stability of these compounds on the shelf, because they can last there. We know their shelf life, but we also look at other calculation based methods, like reorganization energy of these compounds through the reaction. So we see how much this compound is changing, and if it's not changing so much in structure during the reaction, then we assume that it will be more stable, because it has to be undergoing in this kind of reactions back and forth thousands of times during the operation time of the battery. So if I move on, how the workflow looks like. First, we have to design a library. So library design by itself is a challenge. So when you think of molecule design, we want to study the molecules, and we don't want to leave out any molecule in the first place. So we want to study the entire chemical space of that molecule. But when we do this, you can design the molecule, and you want to functionalize this molecule. Maybe we call this a core structure or parent molecule. You want to generate child molecules from this, adding a chemical functional group on the molecule. And then we can do this just through a complete enumeration of the chemical space. So we want to put this functional group on the molecule and generate a new class of molecules. And then we also want to duplicate removal. So you don't have to study the same molecule twice and have the same data twice in your database in the end, and see whether this molecule can be involved in a reaction. And for prediction of properties, we perform calculations that's based on force fields and quantum chemical methods. And these are usually related to redox properties, as well as other properties that we get from quantum chemical calculations. For prediction of solubility, we were using a machine learning model that has been developed in my group, which I'm going to explain further, all these subsections in the next slides. And in the end, of course, we have lots of data. So we generate a library, we perform quantum chemical calculations, we perform machine learning predictions on a given set of compounds. And in the end, we have lots of data on the molecules that we generated. And that's why we need a database. And this database has to be a bit professional in the way that it has been built, in the way that it has been maintained. So this database involves synchronization of data for the calculations, extraction of useful data, because usually when you do a calculation, you get thousands of lines of text from an output of a code, but only maybe it's only one line is important for your purposes that you are interested. That's called data extraction. And the reaction pair matching is just combining the reactant and product molecules, because we want to have molecule A reacting with A prime, not with molecule B, because you cannot convert from A to B, completely different molecule, through the redox reactions that we are considering. So let's move on to each of these steps of library generation, calculations, machine learning predictions, and data creation. And starting with library generation, as I said, library generation by itself is a challenge, and it will become more clear if I give you a drawing of a molecule. So in the center that you see, just a molecule with two rings. One is 6-member ring that we call, the other one's 5-member ring, and 2 oxygen atoms on this molecule. So that means that can be involved in a redox reaction. So those oxygens can be protonated and then reprotonated and deprotonated and etc. So multiple times. But what happens if we choose to decorate this molecule with R groups? Because R groups are the chemical functional groups that can change the structure of the molecule. So by removing a hydrogen atom on the molecule, we can change this hydrogen into an R group. R group, for instance, can be a chemically active unit. In our case, it can be, for instance, sulfonate groups for increasing the redox potential and solubility, or phosphonate groups, or ammonic groups, or like a hydroxyl group, so that can be lower the redox potential and increase the solubility. So you can think of it more complex R groups, or more simple R groups like chlorine, single atom like chlorine or fluorine, but also more complex like chains of chemical groups that can be designed as R groups. But nevertheless, the approach stays the same. So starting with the core structure, you can put 1 R group on your molecule, or 2 R groups, or 3 R groups, and you can change the position of these R groups on your molecule. And each time you're generating a different molecule. Different structure means different properties. So in the end, we are interested in the best performing molecule for energy storage. And that's not necessarily that's going to be the core structure. So it may be the decorated structure, but which one of them? And another question is, which one of these structures can be available for us if you want to test them immediately, instead of trying to do extensive synthesis of a compound and seeing that it doesn't work in the real lab. So complete enumeration happens with a systematic approach. But this is just a drawing in the 2-dimensional space on paper. What happens when we move on to 3 dimensions? Well, as you might see here, the problem starts when you consider three-dimensional structures, starting from left. And here you have the original 2D structure of a molecule and a 3D structure of the core structure. And what happens when we have a small, actually, NH2 group added on this molecule? And you can think of NH2 on paper, just NH2, right? But in real, this molecule has a three-dimensional structure, so it is rotational also. So important in alignment with also other functional groups, especially for compounds that contain many functional groups. This kind of 3D geometric rotations can have an effect on their electronic structure of the molecule, which has an effect on the redox potential. So complete prediction of the 3D structure is extremely important for the redox potentials. So once we generate the library of starting on paper 2D and then 3D structures and a real, now we can move on doing calculations on this. We can do optimization calculations in the gas phase, and then we can try to see how we can predict the redox potentials. And exactly that is the topic in the next slide where I'm going to talk. So in here, we show two examples of chemistries that I showed in the beginning of quinones and azoaromatics. Same reaction that is shown on the left that I showed previously. And we see here on the plot on the right, that the vertical axis is the experimental redox potential, whereas the horizontal axis is some kind of descriptor that comes from calculation. Descriptor means this can be, for instance, reaction energy. So the energy difference between the, let's say, the product and the reactant, or it can be in a different descriptor like the frontier orbital energy. In this case, that is shown for the other aromatics at the bottom with the blue. That's the LUMO, so the lowest unoccupied molecular orbital energy of the reactant molecule can be also descriptor. And we try to see which of these descriptors are actually related to the measured redox potentials in experiment. And as you can see here, for two different classes of molecules, quinones and azoaromatics, shown in red and blue respectively, we have two different descriptors that comes from calculations that works pretty fine. And the first one for quinones is the reaction energy. The second one for azoaromatics is the frontier orbital energy, the LUMO energy of the reactant molecule. Now we are using this information to quickly generate the redox potential data on the compounds. Now we have generated the library of compounds in the computer. Now we perform optimization calculations, and now we have a tool to estimate their redox potential, and we have the redox potential information on the library of compounds that we generated. And what is next in line is the solubility. So solubility prediction, I call this prediction, but maybe a better word can be in actually estimation, because we are using machine learning. Can be made multiple different ways. And the way that we are using in my group is, as I said, the machine learning approach. So for solubility prediction, basically what we do is we collect the data of novel molecules that has been experimentally tested and with solubility information recorded in literature. And we collect multiple data from multiple resources, multiple databases, and then we merge this into a single database, and then we use this database to build a machine learning model to predict the compound properties, solubility properties of molecules that are not in this database. So by looking at similarities of the existing molecules that has been tested and new molecules that we have in our virtual library, we try to estimate how our new virtual library compound is going to be soluble in water. And this process has been described in this arrow kind of a diagram. From left to right, collection of experimental data. We develop a model based on descriptors and target properties of the compounds. And then we train this model, a machine learning model, on the data set that we collected. And we evaluate the performance of this model to see, we reserve some part of this experimental data as a test, of course, that I will describe next. And then to see how this model is performing. If this is performing sufficiently good, then we use this model as a prediction tool for estimating the compound properties. But let's look into the collection of data issue in here a little bit. When we look at the solubility data of compounds in literature, you will see that there are different databases available that are shown as circles on the left, top left in this plot. And these data can be coming from different sources, and some of these molecules can be really unique to that data set, but some molecules can be existing in more than one data set. So maybe sometimes 2 or 3 data sets. But in the end, we want to just combine everything under one umbrella of a curated database. Why do we call this curated? Because we want to see, especially for compounds that have multiple values that comes from different databases, which value is the one that we want to use, which value is the more trustable in the conditions of experiments that we aim for. That's why it's called a curated database, and this is an algorithm that is shown in here. Details can be found in the publication that is shown at the bottom left. It is freely accessible. So basically, in simple terms, what we do here is that once we have collected this data, we categorize this data into how much that we really trust data, how much we can use it for the experimental conditions that we aim for. And for this, we use some kind of standard deviation metric for compound that comes from multiple data sets. So if you have 3 data sets for the same compound from 3 databases, so we try to see which of these are really close to each other, and then we then say that, okay, this is probably more true than the outlier data that comes from an alternative database. So after we do this, we have a complete database that is fully accessible, as details are provided in this paper at the bottom left, but also through our group website. So basically, you can put the information of the molecule, like the name or the chemical description, like a Smiles code, such a string of atoms that has been described in the textual format that is shown in the screen capture on the right. Then you have the solubility values that are tabulated. So you can download this data fully, or you can do a search on the molecules solubility data, and that is shown on the right side through our website also. Once we have the data, let's move on. Why not develop a nice machine learning model that we can use this data for future predictions of compounds that are not found in literature. And that's exactly what we did in this work. Again, this publication details are on the bottom left. It's a paper that has been published just recently, and is fully accessible and freely accessible. Basically, what we did in this work is we have the AQSol-DB data, the database that I was describing in the previous slide, and we categorize the data as good data sets, subsets, and maybe not so good subsets. That's according to our work. And we then build, in part of this data, a model that has been trained on different machine learning models. So like random forest, artificial neural networks, and XGBoost, which is also a tree-based model. And we have a consensus model. So we have not a single machine learning model that works on the data, but we have 3 machine learning models that work together. And then we see how this consensus model is actually performing to individual models. It performs slightly better. That's why we have this consensus model. And then we see the performances of this consensus model on the existing data. And then we can then say, okay, this model is reliable, we can use it for our work. So now we have a method that we can predict the solubility of compounds in water that we can use for our compounds in our virtual library. Once we have the data of quantum chemical calculations plus solubility predictions, as you can see, for tens of thousands of compounds, or maybe even more, up to millions of compounds, then the problem becomes a data issue. It's more getting away from chemistry, getting away from material science, but it's become more a data science issue. So that's why we need a good data infrastructure to collect all this data under one umbrella, and then to learn how we can benefit from this data a bit further. And that's exactly what we did. So for the redox compounds specifically, we have developed a database called RedDB, and it is preprint is available on ChemArchive with the link that is shown at the bottom left. This RedDB is a computational database of electroactive compounds for aqueous redox flow batteries, basically for quinones and azoromatics that I have been describing. And this database contains lots of information related to how these molecules are, whether they can be found in literature, their redox properties, but their molecule properties, as well as atom properties, as well as metadata that can be used for understanding through a machine approach how this data can be used further. And of course, the job info, so the information about the calculations, whether this calculation was successfully completed, the molecule optimization has been successful, has it converged sufficiently, do we really trust this output? that comes from the calculation, and same for machine learning model. So how it looks like in real, it looks like a bit more complex in here, as you might imagine, but actually it is not. On the top left, it's just showing a human readable data set. So that means it's just like an Excel table. You can think of that your molecule number 1, you have some properties associated with that molecule. Molecule number 2, some properties associated with that molecule. And also molecule number 1, maybe atom properties. If you have 10 atoms in that molecule, 10 different properties are associated with, so it's easily tractable by humans. The full data record is also available, that is shown on the right side. So it shows how the calculations, how the data has been arranged, organized in the database. So this data is then completely following that FAIR data principles that is called, is findable. So you can find this data online already. It is accessible, interoperable, and reusable. So you can use this data for your own research beyond the work that I have been describing in here for redox flow batteries. Now we have the database under operational conditions. So how can we now move on trying to find the molecules that we can do experiments on? Because we have lots of molecules, we can basically just filter this molecule based on redox potential and solubility, just get a small filtering. That's the easiest way, of course, and we do that, of course. But also, are there also other hidden properties of structure property relationships between the molecules and the calculated properties that we are not aware of? Maybe it's not immediately visible by looking at the data. So then maybe there can be non-linear relationships. So for that, we have developed a tool that's called CAMPLOT. CAMPLOT provides a way for advanced chemical space visualization. So that means you have 2 axes shown in here, and each of these axes contains no real physical information, but what happens is that you have a molecule with some multidimensional data, and this molecule basically from a data science perspective is the data itself. So data representation of a molecule like SMILES string, for instance, carbon, carbon, oxygen, carbon, and then some property, let's say redox potential, let's say solubility, let's say how 3 molar per liter. So fantastic. So these kind of multiple properties, multidimensional data can be reduced into 2-dimensional space or 3-dimensional space to see how these molecules can be grouped. And each of these groups then shows molecules that are similar to each other. And this doesn't necessarily has to be the molecules that looks structurally similar. You expect that some molecules
Dr. Suleiman, you are muted.
Oh, okay. Now you can hear me, I guess.
Yes.
I hope I was not muting since the beginning.
No. It was just a minute.
Okay. So I was telling that with using CAMPLOT, how these molecular islands can be grouped, and how this information can be useful for humans, because sometimes this information not straightforward, especially for molecules that have very different structures that are having similar properties. So this is not immediately available to humans unless we have the data on that molecule. But an approach like this, like CAMPLOT, can also provide molecules that of chemical space of molecules that can be grouped also together, so that, for instance, if you're interested in the dark blue in this plot, then that means maybe that's more redox active molecules that are with high redox potential, with high solubility. So we should move on to those islands of molecules. So this gives us a way to maneuver around the chemical space of infinite chemical space of molecules. How do we know that our predictions of machine learning can be reliable? Actually, they use again CAM plots. So in this plot, for instance, we have seen that the applicability domain of this our prediction model, as this blue shows the color density of the molecules, and red dots are showing the test molecules, whereas the and blue hexagons are showing the training data. So that means that our AccuSol-Pred model, the machine learning model that we use for solubility predictions, are trained on the blue hexagon molecules. So that means if you have a test molecule that is fitting on these blue hexagons, most likely we can predict those test molecule data as accurately as possible. Whereas if you have a test molecule that is far away from the training model, then your predictions can be completely off. So CAMPLOT also provides a way how we can look at the machine learning model performance, how that machine learning model can be used for making prediction, but how reliable, what is the uncertainty in your predictions. So now let's move on. The final bit of my talk, which is the predicted results and the data that comes from computing and AI. Actually, if I put everything into plots like this, so this is basically in the horizontal axis, the solubility of the compounds. The more you're on the right side, the better the higher solubility, and the vertical axis is the redox potential of the compounds. The more at the top or at the bottom of the molecules in terms of high redox potential or low redox potential, they are the ones that we are interested. And in the middle, and the target is an AccuSol DB compound, which is a very well established molecule, and that has been used for organic redox flow batteries, for water-based redox flow batteries. So we use this as a target, and then we try to see how the newly predicted models are aligned with respect to this target. So essentially, for low redox potential compounds with high solubility, we want to be in the bottom right rectangle of this plot. The details of this work further can be found in the publication that has been just recently accepted in Energy Storage Materials with the DOI link provided at the bottom. And after this predictions, after this funnel approach, seeing the best candidates, what about the experiments? Can we really prove that these molecules are really working? Actually, to do experiments, we have to move one step back. We have to find the molecules that are directly purchasable. So that's what we did. We have the RedDB interacting with a large database called Zinc of compound information, but also vendor information. So these compounds can be found, and it is per gram, is per dollar information is tabulated there, is available to tabulated there, which is a very nice database in Zinc. And we see how our data can connect to Zinc database, and then we then do a search of availability information of these compounds, and then we aim not necessarily then the compounds that are at the top of our prediction scheme, but we aim compounds maybe a bit lower in our prediction scale of redox potential and a bit worse solubility than virtual compounds, but directly available. So why not go and directly test these compounds actually? And after this, we find the molecules that we can buy, and we bought around 20 compounds. And we have performed together with our collaborators from Italy. We have performed on experiments on the molecules that are shown here with the CV plot that is shown on the right side. The details again are provided in the paper that is given at the bottom of the slide. So we show that these molecules are actually working in a redox flow battery setup. So the molecules that we predicted computationally, that we searched automated fashion on the vendor databases, and then we tested in our labs ourselves, and we compare already existing literature of compounds that are similar to the predicted ones. And we found a molecule that is shown with a red rectangle on the bottom left with 3 sulfonate groups of an indigo dye that shows pretty promising actually properties for energy storage. So to summarize everything in one slide, I have this slide for you. Again, this slide is a figure that is taken from a recent paper. So here you can see the whole process that has been described, starting with library enumeration, calculations, and vendor search. and the experiments that has been done on 60 molecules. And as you can see, we have started with hundreds of thousands of compounds with library enumeration. We performed thousands of calculations on different compounds. And after vendor search, we have only hundreds of compounds that are available, and we perform experiments on dozens of these compounds. We have a selection criteria, and we find the best electrolyte for energy storage and redoxable batteries. And also in parallel at the bottom, as shown in this plot, is that we have the data. So not necessarily the best molecule that comes from experiments, but also the data of whole molecules that are discovering from a very large chemical space. Now, this wraps up my talk about the redoxable battery molecule discovery. And if I have 5 more minutes, Arun, then I can continue on the organic-based electromaterials. All right. So I have your head shaking. That's a yes. Then just the second section of my talk is electrode material discovery for sodium-ion batteries. But this section is much simpler, and the approach is very similar to what we did for the first section of compound discovery for organic redox flow batteries. Now we are interested in materials, again, organic-based materials that can be used for sodium-ion batteries, but in the solid state as a cathode material. So this is similar to lithium-ion batteries. So what we do is we again find experimental data of these compounds that is shown in the B for the reaction that is shown in A. So we have again like a 1,4-benzoquinone molecule that we can add sodium atom on the oxygen, or a lithium atom on the oxygen alternatively. And you have form a sodiumated or lithiated version of this molecule that is shown in A. And we have collected data from experiments that is shown in B of different groups of molecules. And by using this experimental data, again, like we did for the previous calculations for redox flow batteries, we develop a methodology that is shown in C, that is the vertical axis, the experimental redox reaction of these compounds with sodium atom, versus the calculated, or the horizontal axis, the calculated LUMO energy of the compounds, organic compounds without any sodium atom actually present. And then we develop a calibration equation. We can see that R square is around 0.95, which is not bad. Root mean square error is lower than 0.1 volt. So we can predict the potential of these compounds for sodium storage as cathode materials based on this equation that is shown with the blue highlight. Now, once we have a new calibration equation that we can use for the discovery of compounds for sodium-ion batteries, we have developed a similar approach like we did for redox flow batteries. So we generate systematically a chemical space that is shown here, the basic structures on the left and core molecules on the middle. So we start with 1, 2, 3, and 4 ring molecules, and then we generate a complete enumeration, including the R group functionalized version of these molecules. Now, the table on the right shows how many molecules are we talking about. So in terms of, for instance, number of different core structures, that is what we call, it's about 170. And when we have functionalization of these molecules, small molecules have small number of positions that can be functionalized, but larger molecules with 3 rings or 4 rings, they have more positions that can be functionalized, so more molecules can be generated from that. And as you can see in the table on the right, we have almost like 500,000 molecules that are sort of functionalized, that are the derivatives of the original 170 core structures. So this is a huge number. So we don't want to work on this 500,000 molecules, but what we do is we search them on zinc and see how many of these molecules are directly available. Actually, we find about 326 molecules that can be purchased. So after this, we perform calculations on the best molecules that can be directly purchased. And here you see 2 different plots. The first one on the left is related to the change in structure of the molecule after it is sodium addition. So sodiumation, maybe that's the word that we can name it here. So the root mean square deviation shows how much of your carbon and oxygen atoms in your organic compound is shifting after you have a metal atom attached to it. So we want our molecules not to shift so much in carbon and oxygen positions, because then this molecule most likely will be more stable for detonation or sodiumation reaction. Therefore, we look for molecules that are lying under a certain level of shift Then we have still many candidates for different number of rings, so 1, 2, 3, 4 rings. And on the right side, we have the energy density and the redox potential of the molecule. So we use the predicted redox potential, which is the EQ that is shown in that integral for energy density, is the one that I showed in the previous slide for the calculation of redox potentials for sodium-ion batteries. And we have the energy density, and then we can see how this energy density is changing. Of course, we want our molecules to have large energy density, so we are interested in molecules that are most likely showing high redox potential and high energy density, which are the molecules maybe top right corner in this plot that is shown on the right. With this, actually, I would like to just tell you that all this data and the databases that can be reached in our website directly, in addition to the publications that have been described in here. And my final words are going to be, of course, thanking the people who have been involved, who helped me in developing this research further, and our funders and collaborators from private industry and public funding. So I would like to thank once again Arun and the organizer of this meeting to give me an opportunity to bring this message to you about our work. And finally, to everybody who has been listening to this talk, and I will be happy to answer any questions if they are from the audience.
Okay, thank you very much, Professor. In fact, it's a very good presentation. You have shown you have thrown some light on how to extract the energy materials using the different approaches and using the computational techniques. And it's a very interesting, quite interesting. If anybody is having questions, let us take up a couple of questions. Okay. If not, I have a couple of questions to ask you. What is the role of chain length of the compound on the to extract the energy from it? What is the structure property relation basically?
Basically, when you have small compounds that are usually more reactive and they have more energy density, so they are more preferred for the batteries as cathode materials. It can be for sodium-ion case, or also for electrolytes for the redox flow batteries. But also these molecules are also small, so that means that they also tend to also deform and change shape. And not always correct, let's say, chemical properties such as redox properties. Especially if you want to have a battery, you want to have a positive side and a negative side. In the positive side, usually the compounds that are small that shows more dominance, and then on the negative side, the compounds that are a bit larger, extended chains that show low redox potential. So you have to find both sides of chemistries. So to answer your question, yes, structure, especially the ring size, has a direct influence on the redox potential, which is extremely important for both of the batteries that I showed, but also the solubility. So usually larger compounds are less soluble in any solvent. Small compounds are easier to solvate depending on the functional groups, of course.
One more, Professor. Do you collect the database or you purchase it from the vendors? How will you get the database?
Yeah, so our databases are entirely calculated properties and entirely collected properties from literature. So that means that we develop these databases ourselves. So we don't work with commercial databases.
Okay. So, and the computational techniques also developed by your group. Is that correct?
Some computational methods are developed in my group, yes, especially the part for machine learning part where we make predictions on solubility, for instance, and or the workflow of the calculations that has been developed in my group. But we also use commercial products or open software that's already available to the community for calculation of electronic properties, and we don't have to develop a code for that. I mean, there are fantastic codes around. For us, we are using products from Schrödinger more specifically, and we are using a code called Jaguar for quantum chemical simulations.
Okay, thank you, Professor. Thank you for joining us for the International Conference on Advanced Material for Innovation and Sustainability. Thank you very much.